Hi everybody! Now that you've got your mount controlled by ASCOM, I'm going to show you how you can get rid of this and all the faff associated with finding and centering alignment stars. I'm Dr. Ray and welcome to AstroGadge. So what's plate solving? Essentially, plate solving is the ability to determine with great accuracy where your telescope and mount is pointing based upon an image that's been taken by it. The information obtained from plate solving is passed on to your mount via ASCOM, and it's used to synchronize it without the faff of trying to find 1, 2 or 3 alignment stars, make sure they're centered and then confirm it, and then eventually get the mount to tell you yes, it's synchronized and know where it is. Plate solving does all that for you automatically with a minimum of fuss. Various astrophotography packages such as SG Pro, APT, Nina, SharpCap, whatever, offer plate solving as a feature, but they all rely on interacting with third-party software in order to do this. Examples of this third-party software are Elbrus, Pinpoint, PlateSolve 2, ASTAP and ANSVR. All of these applications contain or access databases, or they call them catalogues, which contain images of the sky in which the celestial coordinates are known to very precise detail. And essentially what these applications do is take an unknown image that's been taken from your equipment and compare it against their database until it finds a match with a given image, and thereby determines what the exact celestial coordinates of your image is. So there are 2 levels or 2 types of plate solving that these packages can carry out. First one is it's called plate solving, or in many cases it's called near solving. And near solving is when you give the software a hint or a clue as to where you think you might be looking, and the application then goes through its various comparisons with its catalogue or database, but it knows where to narrow down its search. So it's quite a quick method of determining a match, but it needs a clue. So you need to think that you're in roughly the right area in order to get that to work efficiently. The second level or type of plate solve is called blind solving, and that's opposite of the first one. That's essentially when you're saying to the software, well, I haven't a clue where it is, I want you to find out. So what the software does is it literally, again, it compares your image to a number of images in its database in which the image scale and the field of view are known, and it basically compares your image sequentially to pretty much everything in its database that matches your image scale and field of view. It takes longer, but the advantage is if you're not sure exactly where you're pointing, it will determine that with great accuracy. So why is this an important feature? Well, the upshot of this is that you can point your telescope to any position in the sky with not knowing particularly where it is, take a picture and let the software blind solve its location. And once it's done that, through ASCOM, the coordinates are passed straight to the mount and synchronization occurs without the use of having to locate and center either 1, 2 or 3 alignment stars. It's done automatically. If you now know the coordinates of a particular target, you can then ask the mount to go to that particular point in the sky because it's already been synchronized. The software will then check that the mount's arrived in the exact location it should do. It will take another photograph, it will near solve it, it will check that it's found a location, and it will effectively confirm it's got there. So it's a very, very useful tool, very quick way of synchronizing the mount, and with a high degree of accuracy, and has implications later on for framing and viewing the same object night after night, particularly when you're doing a long imaging run involving different filters. Before we go ahead and install the files and applications required to plate solve, we need to obtain two pieces of information which are required by the software. First of these is the image scale of the particular configuration of your imaging rig, and the second is the field of view of your particular imaging configuration. To calculate image scale, we use this formula here, which is just simply the pixel size of your camera sensor divided by your telescope's focal length times 206.265. Now, to give an example, we can use the specifications from some of the kit I use. For example, I use an ATIC 460EX, which has a pixel size of 4.54 microns, and I use an Esprit 120, which has a focal length of 814 millimeters. So if we plug these numbers into the equation, then we get the following results. So the image scale for that particular combination of equipment is 1.1 arc seconds per pixel. So essentially that means that one pixel in the sensor covers 1.1 arc seconds of sky. Now obviously if I was to add a focal reducer to the Esprit, then I would need to recalculate using the different focal length. Likewise, if I use a different camera, again I would have to recalculate. So whatever combination of equipment you're using, you will have to do a separate calculation for any given combination. Once you've got these numbers, once you've got your image scales, then take a note of it because we're going to need these later. If you're the sort of person who isn't keen in the arithmetic, there are plenty of online calculators for image scale that you can use, even if you just want to check your results. And one of these sites, a very, very good site, is Astronomy Tools. I'll leave you the website details at the end of the video so you can have a reference for that and you can use it. So here's the formula that we talked about in the previous slide. So again, if we put in my examples and 840, it gives us reassuringly the same value as I calculated. So this is something you'll need to note down. Clearly, if you have more than one telescope or more than one camera, you're going to have to obtain values for each setup configuration that you have. So that's the pixel resolution. The other piece of information that you will need is the field of view that your camera obtains using your telescope. So you will have to also obtain the field of view afforded by your particular setup, your camera setup and your telescope. Again, this is information that you'll need for plate solving. Fortunately, there are again a number of sites on the internet where you can obtain this information very easily. Again, I'll leave you the site address for this particular calculator. And again, you can see that I've fed in the information regarding some of my equipment, and it's coming out with the field of view is 51 times 40 seconds. Now, as I said before, obviously if you have different telescopes or different cameras and sort of mix and match them, you're going to have to obtain again these values for each combination that you use. So again, take a note of this result. We've got the pixel resolution and we've got the field of view, and we're going to need these as we start to set up our plate solving in the astrophotography software. Now that we've got the information we need, we're going to put that to one side for the moment. We will come back to that later. The setup I'm about to show you involves configuring SG Pro for plate solving. Now, all the other astrophotography applications have very, very similar processes of setup. You will have to carefully read their instructions. There'll be some differences, but generally the principle is the same and the information you require is the same. For SG Pro, I'm going to be using PlateSolve 2 as the near solver, and I'm going to be using ANSVR as the blind solver. Now, I'm going to use PlateSolve 2 because SG Pro comes with a version of PlateSolve 2 which has been optimized for SG Pro itself, so I don't need to download PlateSolve 2 as a standalone. It's already included with SG Pro. I hope you get the meaning there. Once I've downloaded the files and shown you how to set the system up, we'll go out to the observatory, hopefully get a clear night, and we'll see this working in practice. So, as we said, we don't need to download the PlateSolve 2 software itself because SG Pro already has that installed in an optimized format. But what we do have to do is to download the star catalogues that PlateSolve 2 requires. So in order to do that, we need to go on the PlaneWave Instruments website. I'll, as usual, give you a link at the end of the video which you can follow here. And the files that you need are kind of buried a little bit. Don't try looking for them here. What you need to do is go into support, into all downloads. And as we scroll down past the list, these are the downloads that you want. I just download both. It seems to work, and if there's a problem with one, you've always got the other to go to. You need to know, I would let the download just perform to its default folder or directory, and you need to know where that is so you can instruct SG Pro later on, but we'll come to that in a bit. Notice underneath these two downloads, there's also the PlateSolve 2 software. Now, as I said, we don't need to download that. You can use it as a standalone, but it won't really work with SG Pro, as I say, because it's not been optimized for it. So we just need to download these two star catalogues. So once the downloads of your star catalogues are complete, it's always a good idea to go to the directories to make sure everything's there that should be there. And in this case, you can see in both these directories there's lots of star catalogue files which PlateSolve 2 will need to perform its functions. Okay, so we're ready to download the local astrometry plate solver. As I said earlier, we don't want to use the remote version as it takes much longer than having all the catalogue indices physically on your computer. So as I say, it's best to use this particular version which your software can access easily. So again, I'll put the the link to this download page at the end of the video, so you can find this easily. So it's really just a question of downloading the software, setup software, and following the instructions. So once you've installed the local solver from astrometry.net, you'll be taken through various phases in the setup procedure like this. So as you can see, it's put the software into a particular folder. I think the best thing to do is just go with the defaults, and it's going to ask you for a port number for it to operate on. I would just leave that port at the default setting unless there's a very good reason for you not to. I find it works fine with that particular port setting on it. And again, just taking through the setup procedure here, and it's extracting the various files. Okay, so it's completed its download various files it needs to start running. So I will let it do its thing now. If we press finish, during the installation it will come up with this particular message here. Now this is where you have to pay a bit of attention and read what it says, because from what I can tell, many people don't read the instructions properly, and this is probably one of the reasons that the plate solving doesn't work. So if you remember from earlier, my particular setup has a field of view of about 51 by 40 arc minutes. So 20% of that works out roughly 10 by 8 arc minutes. So that's the value I'm going to choose for the narrowest field of view, which is asking here. So in that case, let's look down, and I think the best fit there's 8 to 11, which is pretty much bang on. And likewise, the widest field, well, if you were just using the one telescope, you could just simply put in the full field of view. I use a much smaller refractor along with the spree. I use essentially a 61 millimeter 330 millimeter focal length refractor, which gives me a field of view of approximately 2.42 by 2.1 degrees. So again, I can choose that here. 2.42, beg your pardon, to about 2. So yeah, that will do nicely. Okay. Once we've done that, we can now tell it these are the particular indices we need in the catalogue for the software to work with our particular equipment. And again, what we'll see is simply running through the download. Again, this will take some time, so we'll fast forward to when this is completed. Okay, so having fast forward, we can see that the various catalogue indices have been downloaded successfully. So we're ready to go on with the next part of the installation. Alright, so here we are in SG Pro, and we're ready to configure the software for plate solving. We've downloaded the catalogues, we've downloaded the interfaces, so it's just a question of firstly inputting the image scale, which we calculated right at the beginning. And for this particular setup I'm using, if you remember, it was 1.11 arc seconds per pixel. So it's really important that you put the image scale in the feed that into the software, because without that the plate solving will fail. It needs this information to perform this function properly, and a lot of people forget to do this, and then of course the plate solving fails. So once that's done, we can move on to actually start to configure the plate solving itself. Okay, so we've switched tabs now. We're now in the plate solving tab. We need to make sure that our interface is selected correctly. We want plate solve 2. We're going to set the system up so it takes an exposure of 14 seconds at 1:1 binning. So the camera will, this is the image exposure that the camera takes that the software will use to plate solve. In doing this, we can select which filter we want to use in conjunction with this, and we want to make use of a blind solve failover. So in other words, if plate solve 2 is unable to figure out what the image is and where it is, it will use the blind solver ANSVR instead. So we've selected plate solve 2, we've set our exposure. We just simply need to go into the settings, and if we go into file and plate solve and configure catalog directory. So what we're really doing here is making sure that SG Pro knows where the star catalogues that plate solve 2 needs is stored. So you can see here I've previously selected the directory, and the software's saying yes, I've found them. So plate solve 2 is set up, it's ready to go. The next thing that we have to do is to make sure our blind settings are correct. So again, click on that tab, and again we need to make sure that it's a local astronomy version of ANSVR and not the remote one. And again, there are some other settings which you can manipulate. My advice is just to leave these at default. I've personally found no reason to change them. Everything seems to work with these settings. So again, unless you have any real reason to do that, I would leave well alone. And again, once everything's set up correctly here, simply OK it, and that's us ready to test it. Now, in order to test that plate solving is working correctly before we use it in an actual observing or imaging session, what we can do is we can open a previously acquired image, and in this case what I've done is I've opened an image I took of the California nebula using an S2 filter. The image is linear, but it's been stretched. Now if we go to the control tab, you'll notice that solve and sync and solve and blind sync are greyed out. Now we'll come to this later, but the reason it's greyed out is because, as I said, at this moment in time it's not connected to a mount. So in order to test that solving is working correctly, we can simply right click on this image and go to plate solve here. And we're given the option to do a near solve or a blind solve. Now for near solving, what the software has conveniently done is it has extracted the coordinate data and scale from the image as a hint for the near solve. So all we have to do is simply press solve. And we can see that's pretty rapid, and it's come up with correct coordinates and the image scales that we calculated earlier using the equipment which I talked about.
Now you'll notice here that this little box here, it says use these results as a reference image for target. Now this is absolutely a fantastic feature of this software, because when I click it, what it will do in the sequence, it will use the coordinates obtained from this image as a reference to slew the mount to this target. Now that's incredibly useful when you're imaging the same target night after night and you want to get your frame and focus pretty much spot on each time. It really does take the effort out of this completely. There's no taking photographs and then having to, nudge them out here or there to try and match up the frame from previous nights. It just does it, and it does it very, very accurately, to the extent that you pretty much get frame on frame dead on. So incredibly useful. In my opinion, plate solving's worth it for this this feature alone. We get too few good nights here in the UK to spend mucking around trying to frame things. So this feature is a godsend. It saves so much time. So now to test blind solving. So again, what we simply do is we right click and then left click on plate solve. Now when I press blind solve, just to show that we're not cheating here, I'll actually delete these coordinates. And what blind solve does, as we said earlier, is it simply takes an image and compares it against its catalogue of images taken in a similar scale to what we have acquired. As I say, it's pretty much pattern recognition software. So obviously it hasn't got a hint, and again I'm going to take the scale out here. So it will take longer, but let's give it a try. So it's doing its thing. It's trying to compare the image against its catalogues. So we'll fast forward once it's acquired its image and solved it. "99 seconds later, and it's solved this plate blindly. So in other words, it's done this in an absence of any clues, and it's come up with pretty much the same coordinates as the near solve and the same image scale. Now the ability to do this is incredibly important and a fantastic feature when we want to synchronize our mount rather than using alignment stars. So we're happy that the plate solving is working both near and blind. So we can now go ahead and show this working for real in an imaging session.
The weather forecast for tonight looks like it's going to be clear for a change. For the past 4 weeks, where I live in the north of England, the weather has been absolutely appalling. Been lots of cloud, completely cloud bound, lots of rain, lots of snow, and I think you can see this here, evidence of this in the garden with this lake that's forming in the corner there. So this is my 2.1 meter pulsar dome where I keep my equipment permanently set up. It's a bit windy, but let's hope it stays clear and we can show plate solving in action. Hi folks, so here we are inside the dome, and here's the equipment setup I'm using, which we discussed at the beginning of this video. So this is the Esprit 120 ED. That is set up with ZW electronic focuser. It is connected to a Attic 460EX mono camera with an electronic filter wheel and an optic star off-axis guider. The optical tube assembly is mounted onto Skywatcher EQ8R, and in the previous video we talked about EQ dial mounts. You can see here it's an RJ45 connection that connects straight to the hand control. You'll also notice that I'm not using an SD4 auto guider. I'm using ASCOM for auto guiding, but we'll cover that in a separate video. And the mount is connected to laptop in the corner here. What I've also got set up, as I described in a previous video, was a game controller, game handset, which I used to remotely control the mount. It's connected wirelessly to EQ mod, and you can see it working here. So essentially it's working in the declination, and that's it working in the RA axis. So I'm going to use this now to point the telescope at a point in the sky. It can be any point you want, but I'm going to point it in the general direction of Perseus Andromeda. Alright, that's us pointing in the general direction of Perseus and Andromeda. So we're ready to sync the mount. So before we start, it's really important prerequisite that your mount is equatorially aligned and that you have focus achieved on the telescope. You may or will have to fine-tune the focus once you acquire the target. Now you notice that the grey buttons that were greyed out earlier when we were testing this are now active. So what we're going to do is we're going to tell the system to blind solve where it's pointing, because I don't know exactly where it's pointing, I just know the general direction. And then once it's solved that exposure, we'll pass on the coordinates to the mount and synchronize the mount via EQ ASCOM. So let's go. So it's taking a 14-second exposure, so we can see the image it's downloaded and presently trying to solve. So we'll fast forward to this and come back once it's done it. So here we have it. The software has successfully blind solved the photograph it's just taken, and more importantly, it's synchronized the telescope. So ASCOM now knows where the telescope is pointing, so we can now proceed to our target. No looking for alignment stars, no performing contortions to actually look through the viewfinder on an equatorial mount. Everything's done for you. Alright, so we're going to close this window down, and also we're going to close down the control panel and bring back up our sequencer panel. So we simply go to the target. We've already put in the coordinates. The system now knows where it's pointing, so all that remains for us to do really is to tell it to go to the target. So here we go. So as you can see, the telescope's rotating round to point to the target, in this case M31. is rotating the dome. Just getting a good view of it. As you can see, it's adjusting the and it's now taking a frame to confirm it is where it thinks it is. So because it's taking a frame from something that's been given a clue, it actually should be doing a near solve, and here it comes. And it's found a match. So unless I'm mistaken, my friends, that is the Andromeda Galaxy M31. The mount has found it without the need for alignment stars, purely and simply through plate solving, near plate solving, because the mount has been synchronized via blind solving and the coordinates passed on via ASCOM. Okay folks, that's it for this session. Thanks again for watching. I hope you found it useful and informative. If I've got anything wrong or I've glossed over something, let me know in the comments below. If you liked it, don't forget to give us a thumbs up. If you didn't, well, give us a thumbs down too. Don't forget to hit the subscribe button, and I'll see you next time. Meantime, keep watching the skies, and remember, everything works if you let it.
Watch the sky everywhere. Keep looking. Keep watching the sky.